Hello. Um, Welcome everyone to the week 2 of this multivariate calculus course. So, in this session, we would like to discuss some questions based on the lectures in the week 2. So, in week 2, you have seen basically differentiability, how more on partial derivatives. Then you have studied on the multivariate calculus portion, that how differentiability can be extended to higher dimensions, and then we saw chain rule. So we would like to do some questions based on these concepts. So let's start. So my name is Shami and I am currently doing my PhD in partial differential equations from IIT Delhi. So let's start, without further ado, let's start this session. So this is our week 2. So let's start with the question number 1. We have a function given as yx times x square minus y square whole divided by x square plus y square. And this is for all those cases where my x and y are not equal to 0, 0, and 0 when x, y is 0, 0. Okay, so what do you like to find? We would like to find the second partial derivative respect to x and x at the point 0, 0. So to calculate the second partial order derivative with respect to x, fxx at 0, 0, we just apply the definition. So this is fx at 0, 0 is nothing but limit as h tending towards 0, fx at h comma 0 minus fx at 0, 0 whole divided by h. So this is the definition of the second partial derivative with respect to x. So we have to calculate these things. So to calculate this, what we have to do, we calculate these values fx at h comma 0 and fx at 0, 0, these partial derivatives with respect to x. We would like to find these values and we just plug in these values and just try to find the limit. So let us try to find these first order partial derivatives. So fx at 0, 0 this will be just limit k tending towards 0 f k comma 0 minus f00 whole divided by k. So when my fk0 is, if we see the definition of our function, uh, I have to see what is fk0 and f00. So f00 I know is 0 from the definition, and fk0 is again 0 because I have to take y to be 0 and k to be x to be non-zero, and when I take this, I have a denominator to be non-zero. So if we see, we can actually conclude that fk0 is turns out to be 0 only. So limit k tending towards 0, this will be 0 and this will also be 0. So 0 minus 0 whole divided by k. So this limit will be just 0 only. Okay. So similarly, we'd like to find the fx at h comma 0. Okay, again we employ the definition. So this will be limit k tending towards 0, and this is f at h plus k comma 0 minus f of h comma 0, the whole divided by k. So this is our definition of a partial derivative. So when we put limit k tending towards 0, so we would like to find what is the value of my f h plus k at 0 and f h comma 0. But as we have seen here, when we calculate this partial derivative with respect to x at 0 0, we saw that fk0 is 0 0. Is if f k0 is 0 for any k. So this will imply this will be just again 0 minus 0 whole divided by k. So this will again turns out to be 0. So we calculate the partial derivative with respect to x at point h comma 0, and it turns out that this is again 0. So we just plug in these value in our definition of a second partial derivative with respect to x. So we have calculated this first expression is also 0 and the second expression is also 0. So fx00 will again, if we see, so it will be fx at 0 0. This will be limit h tending towards 0, but we have, as we have calculated, the first thing is also 0 and the second thing is also 0. So whole divided by h, and this turns out to be 0 only. So in this case, as we have seen, the second order partial derivative with respect to x at 0 0 will turns out to be 0 only. And to calculate this, what we have did, we just employed the definition, and after employing the definition, just mere calculation only. So that's how you basically calculate the partial derivative with respect to x, the second order partial derivative. And likewise, you guys can calculate the same partial derivative with respect to y only, second partial derivative with respect to y only. So that's how you guys can calculate the second order partial derivatives. Okay, so moving forward, let's look at another question. So I'm taking this time. The next question is, let my function to be equal to x square minus y square. Then for all x and y belonging to R, we would like to find which of the following is correct. Which of the following is correct? Okay, then the things which you like to check is, these are the four options. first thing is fxx plus fyy is 0. And the second thing we have here is fxx minus fyy equal to 0. Then the third thing we have here is fxx plus fyy plus twice of fxy equal to 2. And the fourth option we have here is fxx plus fyy equal to 4. So since the function given here is very good function, so to calculate the partial derivatives, we can just directly uh, differentiate. Like if we want to find the partial derivative with respect to x, what we do, we just differentiate with respect to x and keep the other variable y to be constant. And likewise, when we calculate the partial derivative with respect to y, we just keep the x variable to be constant and just differentiate as we do in the one dimension case. Because the function is very smooth, it's just a polynomial in two variables. So these are very good functions and can be differentiated directly. There's no need to employ the first principles or first definition of second derivative. We can directly calculate. So let us directly calculate the partial derivative. So if I consider the partial derivative with respect to x, so this is just twice of x, and the second term will be 0 because just a y, and we're treating y to be constant only. Then if I consider the partial derivative with respect to x again, so this will be just 2 only. Okay, and similarly we can find the partial derivative with respect to y. Okay, so I would like to find the partial derivative with respect to y. So let's calculate fy. So fy will be, again, the function given is x square minus y square. So I will keep x to be constant this time. So this will be 0, and minus y square will give me minus 2y. And again, if you like to differentiate again with respect to y partially, so this will be just minus 2 only. Okay, so now we would like to check the options, and we also have to calculate the mixed partial derivative. So fxy would be is the same as taking the y derivative of fx, and fx I know is 2x only, so I have to take the partial derivative of 2x, and this turns out to be 0 because this is a function in x, and I'm treating the function in x to be constant only. So finally we have calculated the second order partial derivatives which are possible. Now we would like to see what are the things which could be possible. So if we like to see the first thing, that the sum of fxx plus fy has to be 0. So we can see, let us consider what's the sum. So sum turns out to be 2 plus minus 2 is 0. So fxx plus fyy is 2 plus minus 2, and so this is 0 only. And similarly, if I see, so first option turns out to be correct. Second is and fourth is not correct. And likewise, we can see that if I see the third option, so this will be, if I consider fxx minus fyy, this will be 2 minus minus 2. This is 4. And so the second option is also not correct. And finally, we would like to calculate fx, the third option, whether that is true or not. So this is fxx plus fyy plus twice of fxy. Okay, and this is just 2 plus minus 2, plus 0, and this is 0. So this is not equal to 2. So my third option is also not correct. So the only option which is correct is the first option, which says the fxx plus fyy has to be equal to 0. So first option is correct, and I would like to add one more thing. So those functions which actually have these kind of thing, when if I consider all the second partial, basically the second partial derivative with respect to x and with respect to y, and if I add this and it turns out to be equal to 0. So these things, when kind of these things are happening, these functions have a special name in literature. They are known as the harmonic functions, and they are very useful in the PD theory. Like if you see all the PDs, they all started with these functions. Like these play a very major role if they satisfy this type of property, this fxx plus f5 equal to 0. So these are like harmonic functions, and they are very useful in PD theory. Okay, so moving on. So let's try some more questions to have a better understanding of calculating the partial derivatives. So the function which I would like to consider is, this time u is another function of x and y given as 2x square plus y square minus 2xy. So what I would like to do, I like to find the value, then find the value of x del u by del x plus y del u by del y is, so to find the value. So let's calculate the value of this. So to calculate this, I have to find the partial derivatives with respect to x and partial derivative with respect to y. So these again, we have the functions which we have considered are very good functions. They are again polynomials in two variables, so I can directly differentiate. When I like to consider the partial derivative with respect to x, I just have to differentiate with respect to x, keeping the other variable to be constant. So let us find the derivatives, partial derivatives. So del u by del x. So I just have to differentiate with respect to x, keeping the y variable as constant. So this first thing will be 4x. This thing will be 0, and this is my twice of x. Sorry, twice of y. So this is 4x minus 2y. And similarly, del u by del y, if I calculate, this turns out to be 2y minus 2x. Okay. So then I have to find the value. So I have to consider del u by del x plus y times del u by del y. So this would be x times 4x minus 2y plus y times 2y minus 2x. So this is 4x square minus 2xy plus 2y square minus 2xy. So if I simplify, this is 4x square 2y square minus 4xy. So I've just clubbed the terms. Now I can see, can also take a 2 factor out of this expression. So this will be twice of 2x square plus y square minus 2x of xy. But if I see this expression in the brackets, this is nothing but my function u only. So this is just twice of u. Okay, so ultimately this expression turns out to be twice of our original function only. And I hope that's clear. So moving on, let's try some more questions. And this time I would like to have some questions which uses the chain rule. So like in lectures, we saw chain rule, how we use the chain rule to find the derivative, partial derivatives, when basically when we calculating the derivative with some variable, those variables are also again have some dependencies. So based on that, let's try one more question to have a hang of the chain rule. Okay, so let my function u to be product xy, and where my x is e raised to the power of t minus e raised to the power minus t, and y is e raised to the power of t plus e raised to the power of minus t. So what do I have to do in this question? I would like to find the derivative, then du with respect to t. So since u is a function x and y, but x and y are further functions of t, so I would like to find this. So basically u turns out to be a function of t only. So I would like to do the total derivative of my function u with respect to variable t. And that too I want at this point t equal to 0. Okay, so let's we know that we have our function u, and it has two independent variables x and y, and these x and y are again have dependencies on a variable t. Okay, so to apply the chain rule, the du by dt would be, this time this thing will give me del u by del x, and this branch will give me del u by del y, and this is a single variable, so this will give me dx by dt, this will give me dy by dt. Okay, so we would like to apply the chain rule here. So this would be just a del u by del x into dx plus dx by dt plus del u by del y dy by dt. So this is just a chain rule. So let me write here, this is chain rule. So I have to just calculate these four derivatives. So I see my u function is x and y, so I can directly calculate, since u is equal to x and y, x times y, del u by del x would be y only, and del u by del y would be x. But yeah, not that, and also we know that x is given as e raised to power of t minus e to the power minus t, and y is given as e raised to power of t plus e raised to, raised to the power of minus t. Sorry. So so what I would like to do, I would like to write these partial derivatives in terms of t only, because at the end we are differentiating with respect to t. So at the end I want my expression to be in t only. So del u by del x will turns out to be y, and y is given as e raised to the power of t plus e raised to the power minus t. And likewise, I can write my del u by del y as e raised to the power of t minus e raised to the power of minus t. Okay, so I got my partial derivative with respect to u, with respect to x and y, and I have to find these variable dx by dt and dy by dt. These variables I have to find. So let's find dx by dt. So this will be e raised to the power of t plus e raised to the power of minus t, and similarly dy by dt would be e raised to the power of t minus e raised to minus t. So thus du by dt would be what? This would be product of these things. So it would be et plus e minus t whole square plus e raised to the power of t minus e raised to the power minus t whole square. Okay. So now I have to calculate. So this is my derivative of u with respect to t. Now I have to find the derivative at t equal to 0. This would be 1 plus 1 square, 1 minus 1 square. So this will be just 4 plus 0, and this will be just 4. So that's how you have to calculate the du by dt at t equal to 0. You just have to apply the chain rule, and chain rule you can make this particular diagram, tree diagram, and that with this diagram you can directly write the chain rule expression. It's one of the easy ways to write the easy ways to remember the chain rule, and once you know the chain rule you can easily calculate these derivatives. Okay, so next, one more thing which we have studied in the this week 2 lectures is this approximation things. So what we basically do, if we have a function, so if we have some small change in our function, basically due to some change in the variable, small change in the variables, so we can get this approximation, get the change, the actual change in the function can be approximated by the change with the help of the partial derivatives. So basically, if we have a change in our function, so we basically approximate it would by the total differentiable of our function, which is nothing but just some sort of that thing, fx del x and fy del y. So this is something which we have seen in the theory. So we would like to see the change in the function can be approximated with the total derivative of function f, and that is given by this expression. So keeping this in mind, we would like to try one question. So to have a more clear idea how to use this approximation ideas. So uh, so the question is, find the approximate value of square root of 399 square plus 302 square. So I have to find the approximate value of this function. But as I know that it is not easy to calculate the square of 399 and then the square of 302, and even if we calculate, then it's very tough to calculate the square root of the whole expression we get. But we know one thing for sure, that 399 is close to 400 and 302 is close to 300, and I know how to calculate the square of those numbers, and that can be easily calculated. So here we would like to use this idea that that 399 is very close to 400, and similarly 302 is very close to 300. So there's not much any difference there. So we can calculate. So if we use this idea of approximation, we can have an approximate value of this square root. Okay, so let us try to find this approximate value. So for this I have to define one function. for that, I will define my function as fx equal to x square plus y square. Okay, and then I know that the initial point which I would like to take, where I know I can easily calculate my squares, so that would be x equal to 400 and y equal to 300, right? So these squares I can calculate. So my change in my x is -1 because I have to go 399, and my change in y is 2 because I'm going from 300 to 302, so that's a twice jump. Okay, so what would be the approximate change? The approximate change df, which is fx del x plus fy del y. So I have to calculate these partial derivatives in order to find this approximate error. So fx would be, if I differentiate this function with respect to x, partially differentiate, this would be square root of x square plus y square, and this is 2x. So you guys can calculate. This is from, so this comes because this is just a square root, so I know how to handle the function which I have power. So when you calculate, this turns out to be the derivative, and this is 1 upon 2 root x and twice of x. So this turns out to be x divided by x square plus y square. And likewise, what can I do? I can calculate the partial derivative with respect to x. So this would be, since there is a symmetry there, so we can expect the same value would be there, but with the variables interchanged, it would twice of x square plus y square into 2y. So this would be y divided by square root of x square plus y square. So now we have calculated our functions, and moreover, what I have to do, I have to calculate these partial derivatives at the value at which I have to calculate my function value. So fx I have to calculate at 400 and 300, because at that point I can find my value of the function. So this would be 400 whole divided by square root of 400 square plus 300 square. So this would be 400 whole divided by, so if we say this is just 16 1,60,000 plus this thing, and this you can calculate. So this would be just 400 by 500, which is nothing but 4 by 5. Similarly, when I calculate fy at 400 300, so this would be 300 whole divided by, again, the same expression in the denominator which we have calculated earlier. So this would be 300 whole divided by this thing. This thing turns out to be 500. So this is 3 by 5. So my df would be 4 by 5, and the change in x, we have seen the change in x was -1 plus 3 by 5 times the change in y, which is what? That was 2. So this turns out to be 4 minus 6. So this is 4 minus 4 plus 6. This will be plus 2 divided by 5. So I know that the change in f is approximately df. So this will imply my functional value at what is this? This is 399 and 302. 399 302 would be approximately equal to what? My functional value at 400 and 300 plus df. So what is my functional value at 400 and 300? This is square root of 400 square plus 300 square plus my change is 2 by 5. 2 by 5 is 0.4, right? And this I we have calculated earlier. This is nothing but 500. So 500 plus 0.4. So eventually this will be 500.4. So the value is the approximate value is 500.4 for this value. And what is this? This is, so therefore the approximate value of 399 square plus 302 square is approximately 500.4. So you can see how easily we have calculated, or we have approximated the value of this square root, which if you try to compute by hand, or by hand, turns out to be very difficult. We need some calculators to find the value, but with just help of the calculus and theory, we can have a idea, or quite a good idea of the approximation of this value. So with this, you guys can calculate other functions as well. So this is one of the examples to make the idea clear. So next, let us try to calculate more examples, and more examples of calculating the partial derivatives. And this time, let's go to second order partial derivatives. So let's start. So now we would like to have some more experience on how to calculate the second order partial derivatives. So it's given that my partial derivative with respect to x is given as both to be 0, and again we have fx at 0 comma y given to be y, and fy x comma 0 given to be twice of x square. So if these values are given to us, what we would like to do, then at 0 0, the value of fxy plus fyx equal to 1 is what? So we would like to find the value of this. So to find this, again we apply the definition. So I have to consider fxy at 0 0. So this notation implies this is fx, the partial derivative y of the function fx at 0 0. So this is what? This is limit k tending to 0 fx 0 comma k minus fx 0 comma 0 whole divided by k. So the value of these things, these are provided in our question. I have to just plug in these values. So this is given as to be k only, and this is 0 whole divided by k. So this is 1. Likewise, let's try to calculate the other derivative, fyx at 0 0. So this will be fy at x at 0 0, limit h tending to 0. So just apply the definition of the partial derivative with respect to x. So this would be fy for the at function fy. So fy h comma 0 minus fy at 0, 0 whole divided by h. So limit h tending towards 0. So this thing would be again given as to be 2x square. So this would be 2h square, and this is given to be 0 whole divided by h. So this is nothing but limit h tending towards 0 twice of h, and when I calculate this as h tending towards 0, this is nothing but 0 only. So this implies that my fyx at 0, 0 is 0. So what do I have to find? I have to find the value of fxy at 0, 0 plus fyx at 0, 0, and I have to add these values. It is 1 plus 0. So this will be 1 only. Okay, so that's how you calculate the partial derivative vectors. You just have to apply the definition. So I think so far so good. So moving on, let's have one more question, which is more what I would say holistic in nature, and that in which we have to like use all the ideas which we have encountered so far. So let me write the next question first. So question number 7 is given as f is a function from R2 to R. Fxy given as mod of xy. Then what I have to do is then at xy equal to 0, 0. What do I have to check? I have to check. I have to see these things, whether these are correct or not. So f is not continuous. The second thing is f is continuous, but fx fy does not exist. Fx fy exist, but f is not differentiable. And finally, f is differentiable, so I have to then check all those properties from starting with the continuity to partial derivatives to eventually to the differentiability. F is differentiable. Okay, so first of all, we have to check the continuity at 0, 0. So our function is given as mod xy, and I have to check continuity at 0, 0, right? So that means continuity at 0, 0, I have my modulus is of square root of x square to the y square is less than delta, and I have to choose delta anyway, so that for any given epsilon I have my functional modulus value to be less than epsilon. So if I see this thing mod of xy, this can be written as mod x times mod y, if we see, and eventually we can write this as less than x square plus y square times x square plus y square. So this is can be written as, because mod x can be written as square root of x square, and this thing is always less than equal to x square plus y square. And likewise, we can do the same thing for others. We have seen these type of calculations in week 1, so there's no need to explain too much in here. And this thing is x square plus y square, and this thing is less than equal to delta square, and I want this to be less than epsilon, and this thing holds if we take delta to be square root of epsilon, which is positive, then square root of x5 will be less than delta square, which is epsilon only, whenever my square root of x square plus y square is less than delta. Whenever where my delta is given as square root of epsilon. So this gives actually continuity over a function at 0, 0. So the first option is not correct. Function is continuous. So next we have to see f is continuous. So second option could be a possibility, but they are saying the partial derivatives doesn't exist. So let's try to calculate the partial derivative with respect to x and y of this function. So again, I'm writing a function fxy is given as mod xy. So then del f by del x at 0, 0. So this will be limit h tending towards 0 f h comma 0 minus f0, 0 whole divided by h. Now what is fh0? This is 0 only, right? This is limit h tending towards 0, 0 minus 0 by h. This is 0. And likewise, if I need to calculate the del f by del y at 0, 0, this will be limit k tending towards 0, f0 comma k minus f0, 0 whole divided by k. This is limit k tending towards 0. But again, functional value at k 0 comma k is again 0. So this is 0 minus 0 whole divided by h by k, sorry. So this will be 0 only. So again, partial derivatives are existing, and we actually calculate their values as well. And their value is nothing but 0 and 0 only. So again, we can see that the second option is also not correct. The partial derivatives are existing. Finally, you have to check whether the function is differentiable or not, right? So whether f is differentiable or not. Or let me better write it, is f differentiable. Is f differentiable? So we know that then to check the differentiability in higher dimensions, we can either adopt a definition, or we have seen one equivalent form to another differentiability. And what's that? So what that is, that f is differentiable at x naught comma y naught if and only if this limit rho tending towards 0 delta f minus df whole divided by rho, this limit has to be 0. And what is my delta f. This is f at x naught plus h, y naught plus k minus f at x naught comma y naught. df is a partial derivative of x with respect to x at x naught y naught into dx plus partial derivative of y at x naught comma y naught into dy. So here the changes which I'm considering are h and k only. So this will be h and this will be k only. And finally rho is nothing but square root of h square plus k square. So this is the definition of differentiability in higher dimension, and this is the equivalent definition. So to check differentiability, I have to just calculate this limit. So let us calculate this limit. And my point is 0, 0 only. So the delta f is nothing but fhk minus f0, 0. So this will be mod of hk. And the next thing is df. We have calculated the partial derivatives, which turns out to be at 0, 0 turns out to be 0 only, both the partial derivatives. So 0 times h plus 0 times k, this will be 0 only. So the limit which I have to calculate, limit rho tending towards 0, this will be hk minus 0 whole divided by square root of h square plus k square. So I just have to calculate whether this limit exists or not. So there are multiple ways to calculate this limit, which we have seen in our first week. So either we can go with the first principles or we can do the polar transformation. So let us try the polar transformations. So we have to put h equal to r cos theta and k to be r sin theta. So this limit will be same as limit r tending towards 0 r square mod cos theta sin theta all divided by r only, right? So this is just limit r tending towards 0 r times mod cos theta and sin theta. So this is 0 only because this cos theta and sin theta is bounded. Now this thing is bounded. So the limit which you calculated turns out to be equal to 0 only, and that's the criteria for the differentiability. And since we are able to calculate this limit and this turns out to be equal to 0, the function is turns out to be differentiable at 0, 0. So this implies that f our function f is differentiable at 0, 0. And what was our function? Our function was given as mod xy. And you see a very dramatic change when we move from one dimension to higher dimension. We see that the function f, let's say f1, x given as mod x, this is not differentiable at x equal to 0. But as we move to higher dimensions, what we are seeing that this type of similar analogously generalized function fxy equal to mod xy is differentiable at x 0, 0. So this is something which you can see something weird happening in higher dimensions, but something which you guys can see something interesting here happening. Okay, so finally, this will imply that the function which we have here is a differentiable, so the option 4 is correct. Okay. So let's continue our session. So next, again, we would like to have a So let's have one more question based on the approximation thing. So that we have a better understanding how to use these approximation things. So let's have a question on based on that approximation theory. So let my function given as y square plus 2y square x minus 3x plus 6y. So using total differential the approximate change in the value of f from p01 to q point 2 1.01 is so we what we are doing, we have our function given as this multivariate polynomial, and using the total differentiable I want to change what's my approximate change in the value of my function if I move from one point to another, where my points are given as 0 1 to 0.2 comma 1.1 1.01. Okay, so I have to find the approximate change. So find the approximate change. I know that approximate change is given as df, and df is nothing but my partial derivative with respect to x at the point which I'm calculating, and then we have a change in x and then change in y. So the point x naught y naught is point p, which is 0 1, and my change in x is 0.2 minus 0, which is nothing but 0.2. And similarly, the change in y can be given as 1.01 minus 1, which is 0.01. So let us calculate them partial derivative with respect to x. So del f by del x. So we again find the partial derivatives in just a normal sense. That is again a good function we can directly differentiate with respect to s, keeping the other variable y as constant. So this will be 2y square minus 3, and del f by del y would be 2y, and for yx plus 6. So we would like to find this value at 0.01. So del f by del x at 0.1 would be 2 minus 3 minus 1, and del f by del y at 0.1 would be 1 twice of 1 plus 0 plus 6. So this would be just 8. So the approximate change df would be del f by del x, which is minus 1, and then change in x is given as 0.02, 0.2, and 8 times change in y is given as 0.01. So this will be just nothing but, if we calculate, this is minus 0.12. So this is the approximate change which I get if I move from point P to point Q. Okay. I think it's pretty straightforward. You just have to plug in the values. As long as you know the values or formulas, you just have to plug in the values and just compute. That's all you have to do. So let's we in theory we also studied one more thing, which is the implicit differentiation. So implicitly means I am not directly expressing the dependent and independent variable relation directly. They are just given in as a implicit form. They are not directly written. So that's the implicit form, and we like to take the derivatives in that particular way. So let's have one question based on the implicit differentiation. So let xy plus yz plus xz equal to 1. Then zx at 1 1 comma 0 is given as, you have to find it. So implicitly differentiation is just nothing. You have to differentiate and directly in a way that we have given the other variables assuming to be independent. So let's say I have to find the partial derivative with respect to x. I'm assuming that z is a function of my x and y. So when I implicitly differentiate, I just like differentiating directly, you can say. So if I differentiate xy, so I know that so I basically have this expression. So I differentiate partially with respect to x. So when I differentiate partially with respect to x for the first expression xy, this would be y only, because 1 times y. Then y is when I differentiate with respect to x, y is independent or can be treated as a constant. So this will be y times del x of z. And finally, if I differentiate, I have to apply the product rule here. So this will be 1 times z plus x times zx equal to, and then 1 is a constant, so this is 0 only. So this will imply y plus y times zx plus z plus x zx equal to 0. And this can be written as, eventually I have to calculate the zx at 1 1 0. So at 1 comma 1 comma 0, this would be 1 zx 0 plus 1 times zx equal to 0, and this implies twice of zx plus 1 equal to 0, and this implies that zx has to be equal to minus half. So you just have to directly partially differentiate. Just differentiate normally and you will get the values. Just keep in mind when differentiating, the which variables are independent, which variables are dependent. We can say that this value is correct if we also can see that since the expression given as to be xy plus yz plus xz equal to 1, this implies that z can be written as, when we compute, basically 1 minus xy whole divided by x plus y. Okay, this is just, I'm taking the xy to be in the right hand side and then just taking the z common and dividing by y plus x. So if I have to calculate the zx, so this would be by using the quotient rule, assuming the y to be independent, just taking the quotient rule of one dimension. This would be the derivative of first thing. So this would be minus y x plus y minus 1 minus xy. And if I take the derivative, this will be 1 only, x plus y whole square. So this is minus xy minus y square minus 1 plus xy whole divided by x plus y square. So this is nothing but minus of 1 plus y square whole divided by x plus y square. Now what do I have to do? I have to calculate this partial derivative at 1 1 0. So I just plug in the values. So minus 1 plus 1 square. This will be 1 plus 1 square. This is, if we can see, this is minus 2 divided by 4, which is minus of, which is the same value which we have calculated earlier. So we can also do these things, but as we can see, the earlier method is more easier to deal with. But it's up to you how do you want to calculate. But that we are doing the differentiation explicitly, but we can also implicitly differentiate. That also can be done. Okay, so moving on, let's have one more question that uses again the chain rule. And this time let's have a chain rule in a more general way. When we have the expressions, the variables which I am differentiating, this is the taking the derivative, has also dependencies on more than one variable. So let's see one example of that. Okay, so let's have a one more example based on the chain rule. So let w equal to function of x and y, where x is given as t times e raised to the power of s and y is given as t times e raised to the power of minus s. Then the value of t times del f by del t plus del f by del s equals. So we would like to find the value of this, but as we can see, the variables x and y are further variables of t and s, so they are more than one variable. So when I have to take partial derivative of f with respect to t and s, I have to be careful. So the easiest thing to deal with things, the chain rule in this case can be get if we just write the tree diagram, and when we write the tree diagram, it's very easy to get the basically exact basically the exact value of the chain rule. So I know my W is a function of X and Y, and my X and Y are again functions of T and S. So if you would like to find the, or I can W or F, it's up to us. So if I have to calculate the value of del F, del D, this would be del F. So let us go back to what it is. This will be del F by del X. From here, this branch I'm getting this, and this branch del F by del Y. And further this will give me del X by del X by del T. This give me del X by del S. And likewise this will give me del Y by del T and del Y by del S. So if I am differentiating respect to T, so I have to consider this branch, how this branch is coming. So this branch is coming from all the way here to here. I have to consider these values. Okay, so this will be del F by del X. And these values will be from at the end in the tree where I'm getting T. So del F by del X times del X by del T plus del F by del Y and del Y by del T. So that's the only two ways from which I can reach T in the denominator in the bottom of this tree. So this is the value. So I have to just calculate these derivatives. So what is my del F by del X? This is just let I test del F by del X because we don't know the exact expression. But what is del X by del T? That I know. This is e raised to power s only. And again, I don't know del F by del Y, so I'm writing this is only. But del Y del T I know. This is e raised to power of minus s. Likewise, let us try to find the del F by del S. This will be del F by del X. Again, del X by del S. That's how I'm moving down the tree. Del F by del Y and del Y by del S. Okay, so del F by del S again I don't know, but del X by del S I know. It is given by TES. And similarly del F by del Y times this will be del Y by del S would be minus T times E minus S. Finally, I would like to find T del F by del T del F by del S. So I have calculated these values. I have just to plug in these values. So let me plug in these values. So it will be t del f by del x e raised to power of s plus del f by del y e raised to power of minus s plus del f by del x t times e raised to power of s plus del f by del y minus t times e raised to power minus s. So I can see these terms are cancelling out. So this will eventually give me twice of t e raised to power of s del f by del x. But what is t times es? This is nothing but my x only. So this is 2x del f by del x. So that's the expression which we like to have, and that's how we basically calculate. I hope the chain rule is clear. You just make the tree and just find the what are the possible ways to reach with respect to t. So there are the two ways which we can reach to the t which, so just follow the paths from the tree from bottom to the up, and just that these are the two paths, and these two paths will give me the value which come in the chain rule. So let's continue, and till now we have seen just only one example for differentiability. Let us compute more examples of differentiability, because differentiability in higher dimensions is little bit difficult, I would say, than the differentiability in one dimension. So to have more examples of calculating the derivative in higher dimension will give us the confidence, and also able to solve, or be able to clear the higher dimension differentiability more, if we have, let's try more problems of differentiability. So discuss the differentiability of the following function at 0 0, where the function given as x sine 1 by x plus y sine 1 by y if xy is non-zero, and if xy equal to 0. So I have to discuss the differentiability again. As I told in earlier question, to find the differentiability, we just have to compute the limit. That particular limit rho tending to 0, change in f minus df divided by rho. This has to be 0 for differentiability. So first of all, let us calculate the partial derivatives. And we have to check the differentiability at 0 0. So I have to compute the partial derivatives at 0 0 only. So del f by del x at 0 0 would be limit h tending towards 0, f h comma 0 minus f00 whole divided by h. So this is f at h comma 0. If we see, it has a 0 because my product is 0. So this is limit h tending towards 0, 0 minus 0 divided by h. So this is 0 only. And similarly, if we calculate del f by del y at 0, 0, this is limit h tending 0, 0 comma h minus f00 whole divided by h. But again, the product is 0. So this is limit h tending towards 0, 0 minus 0 by h. So this would be 0 only again. So my df, which is fx at 0, 0, h plus fy at 0, 0 times k, this is a 0 only. And what is my change in f? Change in f is given as fhk minus f00. So again my product fhk, f00 would be 0, but hk would be this thing. So let us write. So this would be h sine 1 by h plus k sine 1 by k. So then limit rho tending to 0 delta f minus df by rho would be limit rho tending to 0 h sine 1 by h plus k sine 1 by k minus 0 whole divided by root of h square plus k square. So I have to see whether this limit turns out to be 0 or not. So one thing let's try different paths. So rho tending to 0 implies under root of h square plus k square tending towards 0. So if we take the path h equal to k, this will be limit h tending towards 0, or let's say k tending towards 0. This will be k times sine 1 by k plus k times sine 1 by k whole divided by under root of k square plus k square. So this is nothing but limit k tending towards 0 of twice of k, and this is nothing but root 2 mod k sine 1 by k. And we can also take the specific part. Let's take and this is the positive square root, this is just k only. So limit k tending towards 0, let's say 0 from the positive side, so this will be root 2 k by k sine 1 by k, and this is nothing but limit so we can just choose the path that already from the positive side. If it's existing on the positive side, it will be root 2 sine 1 by k. But I know that sine 1 by k does not exist as k tending towards 0. This will create issues, so this does not exist. So eventually this limit does not exist. And since this is not 0, this is not equal to 0. This implies my function is not differentiable. F is not differentiable at xy equal to 0, 0. So let us calculate another differentiability of one function. So I would like to discuss the differentiability of the following functions at following function basically 0, 0, then the function I'm given as fxy equal to xy whole divided by square root of x square plus y square if my x, y are not equal to 0, 0 and 0 when my x and y are equal to 0. Okay. So I had to check the differentiability, and again what we can do to check the differentiability, we just again apply the same definition. So first of all, let us calculate the partial derivatives. Fx at 0, 0, so it will limit h tending towards 0. It will be f h comma 0 minus f 0, 0 whole divided by h. So as we can see, when my product is 0, the function is again 0. So this will be limit h tending towards 0, 0 minus 0 divided by h. So this will be 0 only. And likewise, if I calculate the partial derivative with respect to y, so this time, so if I consider the partial derivative with respect to y, so again this will be limit k tending towards 0, f 0 comma k minus f 0 comma 0 whole divided by k. And again I see the product is 0, so the function will take value 0 only. So this will limit k tending towards 0, 0 minus 0 whole divided by k, and this will be equal to 0. And so we have the partial derivative. This will imply my df is nothing but fx times dx plus fy dy, and dx is my h, this is my k. This will be 0 only. And my change in f, the change in f can be given as f at h comma k minus f at 0, 0. So this would be hk whole divided by square root of h square plus k square minus 0. So this will be same as hk whole divided by h square plus k square. Okay, so finally, so I have to calculate the limit rho tending towards 0 delta f minus df whole divided by rho. So this is limit h and k tending towards 0, 0. hk whole divided by h square plus k square, and df we calculated to be 0 whole divided by h square plus k square. So this is limit hk tending toward 0 0 of hk divided by h square k square. So the rule of thumb which I have told in week 1 was that if we see the degree of numerator and denominator, and if the degree of numerator turns out to be greater than or equal to the degree of denominator, oh, I say the degree of the denominator turns out to be greater than or equal to the degree of numerator, so there's a very high possibility the limit does not exist. And the same case we can see that in the numerator the degree is approximately 2 and the denominator is also 2, so this is greater than or equal to 2, so there's a possibility the limit is not existing. So we can see this is actually the case if we take different paths. So let us take the path h equal to mk. So this will be limit k tending towards 0 m times k square m square k square plus k square. This is nothing but limit k tending towards 0 m divided by m square plus 1. So this is the limit turns out to be m divided by m square plus 1, which is dependent on m. So the limit is depending on m, and since this is depending on m, so the limit is not existing. Thus limit rho tending towards 0 delta f minus df divided by rho does not exist, and this will imply the function is not differentiable at 0 0. I hope this is clear. Now let's have one more part. One more question again on the differentiability. Okay, so let's start, and we like to continue, and let's have one more question which actually based on the differentiability of the function. So let's have another function. So discuss the differentiability of the following function at 0 0. Fxy given as x6 minus 2 y raised to the power of 4 whole divided by x square plus y square if x square plus y square is not equal to 0, if x y are equal to 0 0. So again, to check the differentiability, again we use the limit method to check the differentiability. So let us try to calculate the partial derivative first. So del f by del x at 0, 0. So we limit h tending towards 0, f at h comma 0 minus f comma 0, 0 whole divided by h. This is limit h tending towards 0, h raised to the power of 6 minus 0, h square plus 0 square minus 0 whole divided by h. So this is limit h tending towards 0, h cube, and this is 0 only. And let's consider the partial derivative with respect to y at 0, 0. This will be limit h tending towards 0, f at 0 comma let's say k tending towards 0, 0 comma k minus 0, 0 whole divided by k. This is limit k tending towards 0, 0 minus 0 whole divided by k. Oh no, it's not 0. Let's see what exactly is this. So our function is this, so I have to put 0 minus 2 k raised to the power of 4 whole divided by 0 plus k square minus 0 whole divided by k. So this is limit k tending towards 0 minus 2k, and this is 0 only. So again the partial derivative with respect to y at 0, 0 is 0 only. So, and if I check the change in f, this is f at hk minus f at 0, 0. So this will be given as h raised to the power of 6 minus 2 k raised to the power of 4 h square plus k square minus 0. So this is just x raised to the power of 6 minus 2k raised to the power of 4 h square plus k square. So finally the limit rho tending towards 0 of delta f minus df divided by rho is h raised to the power of 6 minus 2k raised to the power of 4 whole divided by h square plus k square minus, and the partial derivatives we have computed, it turns out to be 0 only. So df is 0 only whole divided by square root of h square plus k square. So limit rho tending towards 0 h raised to the power of 6 minus 2 raised to the power of 4 h square plus k square whole raised to the power of 3 by 2. So again we have seen the numerator has a higher degree than the denominator, so there's a higher possibility that the limit will exist, and this which actually turns out to be the case here. So how do we calculate this thing? We can see that h6 minus 2k4 h square, I can use the polar transformation. Let us use the polar transformation. I think that's the easiest thing when we have h square plus k square type of terms. So I'm taking h to be r cos theta, k to be r sin theta, limit rho tending if this time the rho is turns out to be same as r tending towards 0, r is power of 4 r square cos 6 theta minus 2 sine is power of 4 theta whole divided by r square 3 by 2. So this is just limit r tending towards 0, r times r square cos 6 theta minus twice of sine raised to the power of 4 theta. And this is a bounded thing. So again, this limit will exist. So this limit will be 0. So by the polar coordinates, we have shown that limit is turns out to be 0, and this is the criteria for differentiability. So this will imply the function f is differentiable at x y equal to 0 0. Okay, so let's have one more question before we end this session. So next, I would like to have one thing which we have studied over the directional derivatives, but this is one question which says that differentiability is actually more stronger than the directional derivatives. That even if all my directional derivatives exist, this again still doesn't imply that the function is differentiable. So let's start with this question. Question number 14. It's 14, right? Yes. So question number 14. So let fxy to be given as y divided by mod y square root of x square plus y square, and y is non-zero. Otherwise, my function I'm defining to be 0. Then what do I have to show? Show that f has all directional derivatives at 0 0, but it is not differentiable at 0 0. Okay, so let us calculate the directional derivatives first. So I have to take a unit vector. So p I'm taking to be p1 comma p2, such that p1 square plus p2 square is 1. So this is a unit vector. So I have to calculate the partial derivative. So we limit s tending towards 0, f at 0 plus s p1, 0 plus s p2, minus f 0 0 whole divided by s. This is the partial derivative in the direction of p1 comma p2, in the direction of p hat basically. So this is the limit s tending towards 0, f at sp1, sp2 minus f0 0 whole divided by s. But what's the thing we have here is, so you have to see whether p2 is 0 or non-zero. Depending upon, we have different definitions. So for p2 equal to 0, I know that f sp1 sp2 is 0 only. So limit s tending towards 0, f sp1 sp2 minus 0 0 whole divided by is 0 only, because both the numerator is 0 only. For p2 not equal to 0, what we have to find the partial derivative 0 0. This will be limit s tending towards 0, since our p2 is non-zero, so I have to take this value. So this will be sp2 whole divided by mod of sp2, and this is square root of what we have here. We have here s square p1 square s square p2 square minus 0 whole divided by s. So this is limit s tending towards 0 p2 by mod p2 times s, and in the denominator we have s times square root of p1 square times p2 square. If we calculate this, we will get this expression, and this expression is nothing but p2 by mod p2, and I know that this is a unit vector, so this square root p1 square plus p2 square is 1 only. So this is p2 divided by mod p2, and hence the limit is existing. So thus all directional derivatives exist. All directional derivatives exist at 0, 0. Finally, to check the differentiability, so I know that fx at 0, 0, it is in the directional derivative in that is p at f, directional derivative of p at f at 0, 0, where p is 1 comma 0. So this is given as my p2 is 0, but p1 is 1. So in that case, we find the directional derivative turns out to be 0 only. So this is 0 only. And likewise, if I want to find the directional derivative in the direction of y, so 0, 0, this will be d, let's say q hat of f at 0, 0. So where q is given as 0 comma 1. So this can be given as, I see my p2 is non-zero. So this is p2 by mod p2. So this is 1 divided by mod 1. This is 1 only. These are my partial derivatives. So I have to calculate this limit rho tending towards 0, gradient of f minus df whole divided by rho. So this is limit rho tending towards 0. My change in f is given as fhk minus f0, 0. So that is nothing but given as k divided by mod k square root of h square plus k square minus 0. This is my change in f, and df is given as 0 times h plus 1 times k, and whole divided by rho. Rho is square root of h square plus k square. So this is limit rho tending towards 0 given as k divided by mod k square root of h square plus k square minus k whole divided by h square of k square. So we have to see whether this limit exists or not. So again, if we try to see the same idea that what kind of degree we have in the numerator and denominator, so we can see the same sort of degrees there, because I can take the k to be common, and then there is some issue, so I can take some specific path. So let us, for simplicity, take h equal to k path. So this will be limit k tending towards 0, k by mod k h square, it will be root 2k minus k. Again, it will be it will be 2k square. So this is limit k tending towards 0. I can take k to be common. And again, I can take k to be from the positive side. So at least have to remove the modulus expression. So this will be just k times root 2 minus 1 root 2 k this will be root 2 minus 1 whole divided by root 2, and this is not equal to 0. So the limit is not coming out to be 0. But for differentiability, we have to this limit to be equal to 0. So this will imply the function f is not differentiable. Even though all the partial derivatives exist, the function is not turns out to be differentiable. So with this, I guess I can conclude my session here. So I guess in this session we have seen many examples of differentiability. Finally, we are able to calculate differentiability in higher dimensions. Then we see some approximation results, and we also saw some chain rules, chain rule questions. So to solve chain rule questions, you just have to just draw the tree diagram, and just with the tree diagram, you can easily able to write the chain rule for any type of function which you like to have. And I guess we have also calculated the higher order derivatives, and that again are easier to calculate. You just have to apply the definition, and that's all you have to do. So we have pretty much clear how to calculate the derivatives and higher order derivatives in higher dimensions. So with this, I would like to conclude my session of this week. Thank you.